Okay, this is a set of notes on something called an orthonormal basis. We're going to build up from the bottom here. So, I'm going to have S be a subset of V. V is an inner product space. And that's going to be such that for every U in V in S, I want the inner product of U in V to be 0. If this is the case, then S is an orthogonal set. So if all the vectors in the set are orthogonal to each other, then we call it an orthogonal set. Okay, so if I add to this, that if V is in S, then this implies that the magnitude of V is 1, then we call this an orthonormal set. Okay. And then if we add to this that S is a basis for big V, then we say that this is an orthonormal basis. Okay, so that's kind of stepping through this. So let's look at some trivial and some interesting examples of this. So the standard basis 1x x squared x cubed in P3 under the ordinary standard inner product is such that this is an orthonormal basis. So this is an orthonormal basis for P3. Pretty simple, straightforward. We also acknowledge that like C continuous functions from 0 to 2 pi is an inner product space where the integral from the inner product f of g of 0 to 2 pi of f of x times g of x dx is the established standard inner product for this space, right? So the set S equals 1, and then all the signs of the multiples of pi and the signs of n times x, that's what it is. There we go. And the cosines of n times x from n equals 0 to infinity is an orthogonal basis. Now, the problem here is that the norm of each of these is not 1. Okay, so I actually get orthogonal and I get basis for the set of all continuous functions from 0 to 2 pi. Because this is a well-ordered set, its size is infinite, but I know all of the members because I can map the members to the integers. Okay, so it is a countably infinite, well-ordered set, right? So that's kind of an interesting twist on it all, right? So I just go from 0 to infinity and count up, and I get all the members of a basis for the continuous functions. You can check this and see if it actually works, and it's kind of clever that it does. But I don't get orthonormal, so I have to make a little change here to get orthonormal. If I change the 1 to 1 over the square root of 2 pi, and then I put a coefficient of 1 over the square root of pi in front of all the signs, and 1 over the square root of pi in front of the cosines, now, and again, you can go and check this and do all the work, this is orthonormal basis. Each of these has a magnitude of 1 on the interval from 0 to 2 pi, and they're all orthogonal to each other. So this is going to give me, and there's a sufficient number of, like if you give me a function, I can actually make a what do you call it, a linear combination of these things to give you back that function. So that's a little bit trippy, but it does in fact work, and this is kind of putting us into a land of what is called Fourier. So we're going to get another French mathematician in here at some point here, and we might look at some of the Fourier bases and things like that, because this has something to do with the application of pulling signal out of noise and things like that, and so we'll get there. All right, so let's take a look at a quick theorem here and a corollary that comes from it, and then we'll call it a day. Okay, so the theorem here is that if I just have simply an orthogonal set, then, so orthogonal sets are linearly independent. Okay, so this can be proven kind of straightforward. So let's say I have an orthogonal set. So S is V1, V2 to Vn orthogonal. Right? This is going to be my proof. So how do we prove linear independence? Well, we take a linear combination of the vectors in the set, right? So we've taken a linear combination and we set it equal to the 0 vector. Now, if these are linear independent, then it suffices to show that C1, C2 out to Cn all must be 0. Okay, so let's see what we've got here. This means that for every v sub I, which is in I from 1 to n, the following statement is true. The inner product of C1 V1 plus C2 V2 out to Cn Vn of v sub I has to equal the inner product of the 0 vector and the v sub I vector. Okay, so what does this mean? Let's say, okay, so we can decompose this a little bit, and we can say that C1 is the inner product of V1 comma Vi plus C2 times the inner product of V2 Vi plus Cn Vn Vi should equal, well, 0 inner product with anything is 0. Okay, so the first thing that I note is that if Vi is taking inner product with Vj, this has to equal 0 when I does not equal j, because this is an orthogonal set. So quite literally, this sentence is just going to reduce to CI VI VI is equal to 0, because all of the other terms became 0 because they're of the orthogonality. Well, VI, since VI can't be the 0 vector, this cannot equal 0, so this implies that CI has to equal 0. But CI was chosen arbitrarily, so this would have to work for all I equaling 1 to n, which means all the coefficients have to be 0, which ultimately means that I am linearly independent by definition. So there's proof of that statement. All orthogonal sets are linearly independent. Okay, we're going to get a corollary from this that's a little bit more useful than the theorem itself. Okay, so the corollary says that if S is a basis for V in inner product space, right? And the size of set S is equal to n, so S would have to be finite here, right? Then all orthogonal sets of size n are also bases. Now, why is this a corollary? Well, because we just said that if they're orthogonal, then they have to be linearly independent, and if they are size n, and there is a basis of size n, then they have to be of correct size. So, if they're linearly independent and correct size, we get spanning for free. So that would get me a basis. So a quick example here. Okay, so let's take a quick example of this. Let's say that S is the set 2, 3, 2, negative 2, 1, 0, 0, 1, negative 1, 0, 2, 1, and negative 1, 2, negative 1, 1. Now, this is something I'm not going to work out, but this we'll call V1, V2, V3, V4. And in fact, you can check this VI, Vj here is equal to 0 for all I and j equaling 1, 2, 3, 4, where I does not equal j. So this means that S is orthogonal, and with that, since it is the correct size for R4, S is a basis for R4. Alright, so there you go. This is Introduction to Orthonormal Bases. We're on a collision course with the Gram-Schmidt orthonormalization process, which is the other big algorithm that happens in a basic linear algebra course. So we have 2 out of 3 so far. We have Gauss-Jordan, we have the simplex method, and now we need Gram-Schmidt. Alright, so there you go.